Okay, so welcome to today's class. Today is the day 5 of the business intelligence course using Excel and Power BI. Amar, do you want, I think you have to say something for 10 minutes, right? Do you want,
No, that will be done tomorrow, ma'am. So you can directly start with the class.
okay. So Amar, can you please clarify on the LMS issues? There are a lot of people who are complaining on they are unable to download the file in Excel or any other format. The files are only shown as PDF. Can you please
No, ma'am. Whatever the files you shared in Excel format, so
Can you
that
please
upload
show
in.
your LMS or any student's LMS so that they are clear? If you can, if you
Uh,
don't mind. Yeah.
yeah, sure.
Yeah. Amar, you can share your screen if you want. Yeah.
Yes. I'm just sharing my screen. Yes. So suppose that for today's material, which I uploaded, or previous and day one material we want to download. So you have to open your course, okay, and then your material is there, okay. So you can check here. You will be having the option here, download resources. Okay, CSV to Excel. So you can click on that. That will be downloaded. Okay. So in your downloadable files, you can check in a downloads. That will be available there. So today's file also similarly it's uploaded on the LMS board. So you can just check that.
Okay. Thank you, Amar.
Yeah.
So, guys, is it clear? Anyone having any query about how to access the files on LMS? I think this is clarified now, right? Okay. So let's start with the session. So in the last class, I have basically learned about how to use functions, how to use filters, and within the filters, we have used the same basic functions, right? Using subtotal. And then we learned about how to do data validation and basic statistics, how to calculate mean, median, mode, right? How many of you tried any of this at home? Is there anyone who tried it? Okay, so today our agenda is going to be using graphs in Excel. I think this would be quite a topic which perhaps most of you will know. Okay, so our idea is to learn how to use graphs, and some of you are very keen in doing statistical tests, right? So we will do some basic statistical tests like t-test, z-test, f-test, regression and all using Excel. So this is our goal for the day. Okay, learning outcomes. Okay, so the first question is, why does graph matter? You can see on the screen, right? You have a data and you have a graph. Do you think this representation via graph is better than this data table? I want you guys to either use the screen or you can use your mic. Okay, so Bhavana is saying yes. Why? Why, Bhavana? Why do you think this is better? Okay, pictures convey. Okay, so is a graph same as picture? Is a graph same as picture? So I think Manu Francis saying pictures convey a lot more than words. Okay, visualization and comparison gets more attention, easy to understand through graphics, very good. So gets more attention, easy to understand. Comparison becomes easier, very good. Yes. a lay person can understand. I understand this. So now there are two interesting things I want you to tell me. Is visualization same as graphs? Is picture same as graph? These are the two things I want you guys to talk about. Yes. Compact data, okay. Yes, all of these are valid. So another question based on what you have told me is the picture same as the graph? Pictorial form of data, okay. So pictures are not same as graph for your all your understanding, okay. Graph is when we take data and we are basically putting it in a structure, right? These are generally lines. The lines could either be, represented using width, length. It could be the it could be on XY axis, right? These are called as graphs, or it could be in terms of radians. Okay, am I making sense? Manu, Francis, and others. So the difference is that we are not. It's not like we put boxes. Okay, here in terms of representation, you can see that majority of the graphs are structures which would be basically lines or circles. Okay, and the data that we have is going to be represented either in terms of the area or angles or the length, width, breadth, something like that. Okay, these are the variation. Am I making sense, everyone, how it is different from pictures? Clear? Okay. Okay, so the graphs are not same as visualization also. Why? How are visualizations different, guys? How are visualizations different from graphs? Anyone has any idea? How are visualizations different, guys? Visualizations are dynamic. Okay, what else? So, to a certain level, yes. So, I told you, right, graphs have static data. That's very correct. Very good. Visualizations can be updated on the go. So, generally, when we are having these graphs on a dynamic platform like a dashboard, we do call them as visualizations. But visualizations can be pictures. It could also have, different formats. For example, have you seen this man and woman kind of pictures, which is having some kind of area filling and all? These are called as graphs. Have you seen that kind of graphic, guys? So instead of writing a graph, right, or a pie chart, suppose I'm putting a picture of a man and a woman, and instead of saying that 75% of the respondents are male, okay, I will fill the male, that icon 75%. Okay, the female, I will fill it 25%. This is called a visualization. Am I making sense, everyone? Yes, this is neither a picture, neither is it a graph. Okay, this is called as visualization. So you are representing data in a very easy to understand, or to be put in a print or in a web format. Okay, these are called as visualizations. They need not be dynamic only. You can, you can basically, for example, even if you guys have this phone, nothing. Okay, what happens in nothing, guys? So you have certain lights. So if you look at the nothing phone, you will find that it has got some LED bulbs, right? So if someone is sending a message, some combination of the lights will glow. Okay. If someone is making a phone and you put it on silent, right? Instead of vibration, you can have some other combination of these LED strip to glow, right? These are also visualizations. Am I making sense? Visualizations need not have data as the base of it. It could have some rules also. Okay. Am I making sense, everyone? How visualizations are different from pictures, are different from graphs. Am I making sense? To a certain level, pictures which is having some kind of area are visualizations, especially in Excel, in the Excel world or in the PowerPoint world. Okay. Pictures are pictures, and then you have these. This is what kind of graph do you see on the screen, guys? This is what kind of graph? Yes, this is called as a bar graph. Very good. And like you said, you can find that this graph is much more clarifying than this data, because here I know that this data is in descending order. I know what is the difference between the first ranking and the second ranking company and the third ranking company, right? You can see all of that. And it is very intuitive. So one of the most important thing is that a person who is who's perhaps just 8th standard, pass, can also understand this graph without anyone telling him or her anything, isn't it? These are universal concepts. Whereas this data, you can see there is a rank, then there is some data. So a person might find it very difficult to go around it. So here you can see that Google is rank 1 without even putting anything. You can see that it is ranked 1, right? Is it clear, everyone? The advantages of graphs? So it is very intuitive. It is easy to understand, right? And when should you use a graph and when should you use a table? Anyone has any idea? When should I go for a graph? For example, here I would say that in this particular screen, if you see, right, you have this data and you have this graph. I would say that this graph is as good as this table for me, at least. Right? So maybe this is not the best example of a graph. So when should I go for a graph is the question that I had. When should we go for a graphical representation? So whenever you are trying to infer, so I am not just reading out the data, I am trying to infer something much more that cannot be put in a table, I go for a graph. Making sense? Another advantage is you can have a number of graphs on a screen, right, to tell a story. If you cannot have a number of tables on the screen to tell a story. Okay, so that is another advantage. It is our human mind is widely capable of connecting the graphs and create a narrative. Okay, so that is another advantage. Is it clear when I should use a graph? So here you can see that this graph is as good as this data to a certain level. So maybe, here I don't even need this graph. Okay. But suppose I had much more information, I would go for a graph. I will not even show this table. Am I making sense, everyone? Okay, so you can see these are the different graphs, right? I want each one of you to identify the sales table. What kind of graph is this, guys? What kind of graph is this? Line graph, correct. So when do we generally use a line graph? When do we generally use a line graph? Trends. Okay, what else? You can see the trend. What else? Can you see your x-axis is January, February, March, April, right? Or it could be dates. So line graph basically, yeah, not only trend, whenever you are trying to represent data over time or over a period, right? You can use a line graph. Is it clear? Yes? Suppose you want to, here I actually, if I want to compare two quantities, should I go for a line graph or should I go for some other graph? if I want to compare 2 or 3 categories, right? Should I go for a line graph or should I go for something else? I will go for this kind of column graph. Can you see this? So when you are comparing quantities at a period of time, I go for a bar graph. When I compare them over a period of time, you can see here, I can go for a column graph. This is called as a column graph. Okay. So is it clear when I should go for a column graph? Okay. Where else can I use a column graph? Where else can I use a column graph? Where else can I use a column graph, everyone? Yeah, for comparison also, yes. So you can see here, right? Look at the organic search, paid search, social media, this. You can see, right? When I'm looking at components of over time, right? I'm looking at how the proportions are changing over time. Again, here I can use a stacked column graph. You can see they add up to 100, right? So I'm trying to see the changing trends here, right? There also I can use a 100% stacked column graph. Making sense, everyone? Can I use a pie chart here? You can use a pie chart. But can I compare pie chart over time? Yes. So we generally use pie chart under 2 conditions. Okay. Again, like a bar graph, a pie chart you are comparing just at a particular point in time. Okay. So if I'm only having one proportion, like only October is available, I don't have November, December, I can very well use a pie chart here. Okay. And number 2 is, if you are having more than 5 different items, do not use a pie chart. Use a this kind of stacked, or you can see this also, column charts. Am I making sense, everyone? What happens if you are having more than 5 categories or subcategories in a pie chart? What happens? What becomes the issue, guys? Suppose I have 8. Yes, very correct. So you will find that it is going to have different colors, and you will know. See, generally, we try to showcase percentages which are significant in graphs. Okay. Suppose you are having 1%, 2%, 3% and all. It's a good idea to combine them and show them as others. Because it is not easy to interpret. You lose that intuitivity and understanding. Okay. Clear, everyone? Okay. Now we have something called as a histogram. What is this histogram, guys? What is this histogram? What is this histogram? Okay, so very good. I think Sarath, between Sarath and Dell, you are understanding the histogram. So the histogram actually shows me the shape of the data. So what do you mean by shape of the data? We basically find the frequency of the data. Okay. So if you have a line like this, so you can see here you have bars. This means that this data is not continuous data, it is discrete data. I can have a histogram for discrete data also. Okay. But in this case, you have to define the number of bins. So if you're having categorical data, right, I probably will have a frequency table for each of the categories, right? So that is called as a histogram. Am I making sense, everyone? Here you can see I'm having a range of data. You can see, right? More than 80 have basically clubbed everything and have said more, right? This is a frequency data. But suppose instead of having these discrete bins, so here you can see 20 to perhaps 40 is here, 40 data, 40 to something is here, right? So you can see 30 there is no data, 40 I've got some data, 50 there is no data, 60 I've got data, right? So I put a frequency. Suppose instead of this I had 20, 21, 23, 4, 5 data like that. Then we will basically be representing it with a curve. Okay, am I making sense, everyone? So that is basically a histogram for continuous data. So whenever your data changes, the shape of this histogram will also change. Clear, everyone? And basically then it will be called as a frequency distribution function. Okay. And then you will write one function equation and all of that. Basically that means that if you see any kind of line graph and they talk about frequency distribution function, it basically means that the data that you are considering is not discrete, it is continuous. Making sense, everyone? So how many of you know about the normal distribution? How many of you have heard about normal distribution? So how does the normal distribution look like? It looks like this. Okay, so I will have something like this. Okay, this is a normal distribution function. Yes. So this means what, guys? This basically automatically means that the data is it discrete or is it continuous? Is this data discrete or continuous? It is continuous. Very good. So you can see to a certain level, this is also slightly normal. Why is this called as a normal distribution? Anyone has any idea why this is called as normal distribution? What is normal about this? Okay. So this is correct. So these are the characteristics of the normal distribution, correct? It can be divided equally, right? So you will find that basically you will find it is having a mean, okay? And then you have this. These are all characteristics. But why this particular distribution is called as normal is my question. What is so normal about it? Anyone having any idea? Why this is called as a normal curve? No. So what happens is in nature, okay, if you take the marks that people in a class get, or you take the heights of, people in a particular area or in a country, you find that the data automatically is going to look like this. You find that most of the people will have their heights or marks or weight or whatever to lie near the mean within the nearly 66% of the population will have they will lie very close to the average or the mean. Okay. How close? It will have only one standard deviation. Okay. then you will find that nearly 95% of all people, okay, they are going to lie within. So this also includes those who are lying within one deviation, right? They lie within two deviations. That's why this is called as normal distribution. So any data that you are able to measure, okay, whether it is marks, height, weight, ages of uh, babies, okay, in a particular population, anything that you take. Suppose I take the number of days, okay, of the babies. So babies means what? They are within the age of 0 to 5, right? So you will find that automatically all the data will fall like this. It will be symmetric, it is a bell curve, it is going to have one mean, it will have a standard deviation. You will find that 66% of the data will lie within plus or minus one standard deviation. 95% of the data will lie between two standard deviations, and 99% of the data will lie between three standard deviations. That is why this is called as normal data. Is it clear, everyone? Are you guys following me? Why it's called as normal distribution? Yes? Anyone having any questions, query? So this is like, okay, so the only condition is whenever you're looking at data and it should have normal distribution, the sample size should be greater than 30. Okay? Your sample size should be greater than 30. Clear? Everyone? Okay, why this is important? So you will find that whenever you are looking at data, we have something called as qualitative data and something called as quantitative data. Quantitative data means generally it should be more than 30. Okay, this is also the reason we will generally check whether the data is normally distributed, or we will try to standardize or normalize the data, right? All of that means you're working with more than 30 data points. How many of you have lost me? How many of you are following? Raise your hands, people who want me to repeat. Because this concept is very important, okay? Okay, Sahil Khan. Okay, so some people who are raising their hands, let me repeat this. So basically, what I was saying is, if you are having more than 30 data points, okay, what data point? This could be marks or ages or height or weight, any data, okay, that you can measure. That is, it could be continuous. Okay. Suppose you take in this class only, now we have got, let's say, 242 people, right? If I try to get the ages of all of you, right? To a certain level, it will look like this. Okay. So what is the characteristic of this? You will find that most of you will have your ages very close to the average age. Okay. And most of you will fall within one standard deviation. Okay. Then 95% of the people will fall within two standard deviation. And 99% of you guys ages will fall within three standard deviations. Okay. So you will find it's a bell shape. It is symmetric. So you can see it's plus or minus, right? There is one mean, median, mode. It will all be the same. It will be one standard deviation, right? Correct? So this is called as a normal curve, because in nature, whenever you take data and you put it in ascending order, normally the shape will be this. That's why this is called as a normal distribution. Is it clear, everyone? So whenever in database we say something is qualitative, it means that we have less than 30 data points. Okay. Whenever we are talking about normal distribution and all, we should have more than 30 data points. So it's also called as quantitative data. Making sense, everyone? So people who raise your hands and did not understand, have you now got this clarified? What is normal distribution? Yes or no? Okay. What is this graph, guys? This last graph, what is this? This one, what is this? This is a scatter plot or it's a regression? Is this a scatter plot or is it a regression? This is a plot for a linear regression. Okay. So in a scatter plot, you basically are just trying to put the data or the relationship between any two data points. Okay. So you will basically plot the data between these 2 points. Okay. This is called as a scatter plot. And the value of this you can get by using the formula core of. So how can I get the relationship, how much it is? So you can use the formula equal to corel, right? Or core, and then you put the x array and the y array. Okay, it will give you the relationship between this. So this is called as the correlation coefficient, or it is the small r squared. Okay, this correlation coefficient measures the relationship between these two, x1 and x2. Is it clear, everyone? If this correlation coefficient is a line, only then you will do a regression, linear regression. You can see here, for all these dots, it is not a line. There is hardly any correlation coefficient, right? Then I cannot do a linear regression. Is it clear, everyone? So what does a correlation coefficient do? It tells you the relationship between x and y. Linear regression means continuous data. Yes, the linear relation means that my dependent variable. So here you can see I have a dependent variable. This needs to be a continuous data. My independent variable, most of them will be continuous, but I can also have some categorical data. Am I making sense? Surumar Kushali? How many of you did not understand? Raise your hands. How many of you did not understand this correlation? Yes, okay. So basically, whenever you are having two sets of data, okay, I'm having x1 and x2 and x3, right? I want to see how x1 is related to x2. Then what I will do, I will draw a scatter plot. So in a scatter plot, I basically just have x1 and x2 as x and y axis and I start plotting it. Okay. So what I am essentially plotting, I am plotting what is called as the small r squared, which basically tells me that if x2 increases, is x1 also increasing? That is all it is measuring. This correlation coefficient, it measures the direction in which x1 moves alongside x2. Suppose x1, suppose the relationship is like this. What does this mean? Suppose the relationship between x1 and x2 is like this. What does it mean? It means that when x2 is increasing, x1 is decreasing. Can you see that? As my x2 is increasing, you can see my x1 is decreasing, correct? Yes or no? How many of you are following, right? So here you will find that it is having a negative relationship. Okay? So this small r squared, which is also called as the correlation coefficient, it is going to lie between -1 and +1. The best is x1 is increasing in the same rate as x2. The worst is x1 is decreasing in the opposite rate as x2. So it will lie between -1 and 1. Is it clear, everyone? This is called as correlation. Clear? Okay. Now, whenever you are doing a correlation, right, it is a number. So here you can just say correl and you enter the two arrays, it will show you a value. But always draw the graph. Why you should always have your graph alongside your correlation coefficient, guys? Anyone having any idea why it is a good practice to do this? Because you do not know whether this is how all the data is or it is just one data which is behaving like this. Suppose you have something like this. Okay. You remember we had this case where you had a very rich person in your colony or you had a very poor person in your parent. So let's say you have one person who's here. Okay. Everyone else is here. So you can see that there is only one x2 value for all x1 values. One data is the outlier. Okay. Now this outlier is influencing so that I have a negative R2. Correct? If this data was not there, then what kind of correlation I will have? I will have a zero correlation. Yes or no? Am I making sense, everyone? So this is the reason that you should always put a scatter plot alongside an R squared to understand the relationship between two variables. Just getting the value is not good enough. Just getting the graph is not good enough. You should always see both of them together. Okay, clear? This is one of those cases where you need to have the graph alongside the value. If you find that there is a linear relationship, what is a linear relationship? How do you identify the linear relationship of correlation, guys? What is a linear relationship look like for correlation? Tell me. So whenever you have a linear relationship, right? So you will have data like this. You can basically, you have a correlation, okay? It will lie like a line. Almost all the data you can see are nearby this line, okay? Only if you have something like this, I can try to fit a linear line as a regression, okay? If suppose the data is like this, okay? So you can find it's no longer a line. It looks like a curve, okay? So if you have a correlation like this, then I cannot fit a line. What I have to do then, I'll have to divide the data into three parts. So I'll take this data, then I'll take this data, then I'll take this data. Am I making sense? Okay. So what I was trying to say is, so before you do linear regression, you always basically do a scatter plot, right? So you will look at not only will you look at the R squared value, you will also look at the shape of this graph. Okay. Can you see the shape of this graph? How does it look? What is the shape of this graph? You can see it looks like this, right? Yes. So if it looks like this, then I cannot fit a line to it. I can fit a curve to it, right? So I will, this is called as, this is not an inverse S. This is called as a polynomial regression. I will try to fit a polynomial regression. I cannot fit a line. If I try to fit this kind of regression, it is wrong. Is it clear, everyone? Making sense? So if I want to fit a line as a regression, then what I will have to do? I will have to draw a line using this correlation and see the shape of the line. Okay. Here, definitely, I should not try to fit this kind of linear regression. I have to fit a polynomial regression. Clear? No. So actually, you can see that in this particular line, right? You can see there are basically you can see that there is here one line, then it goes down, another line, then it goes up again, third line. You can see the shape of this line and this line are very different. So I can't even combine them. Yes. So I will have to divide this data into 3 parts and then I will try to fit, which is all very complicated. Ideally, I should just fit a polynomial regression. So it will be a polynomial means what? It will just be some kind of curve. Rather than fitting a straight line, I will fit a curve. Is it clear? Logistic regression into non-continuous data. What is this? Kushali, I did not understand your question. Okay, so what is a logistic regression? Okay. Okay, so in a logistic regression, what is going to happen is, so you have something called as a dependent variable y, okay? So you will have 1 and 0, okay? Then you are going to have x values. So let's assume that x is, for example, let's say you have a Airtel phone number, okay? So you have x. So basically, you are using this data, right? This data on your Airtel. How many? So whether you are going to keep this phone or not is going to directly depend on whether how many times you are calling your customer care. Why? Because generally the people who keep calling customer care are the people who are facing difficulties. Correct? These are people who basically are facing difficulties, right? So you will find that, so in a logistic regression, what we are trying to do is, we basically are having your dependent variable to be of 2 parts. Either you are going to keep the number, which is 1, represented as 1, or you are going to give away your number, which is represented by 0. Okay. So you basically find a point of x. So it is possible that generally people who keep calling, right? I might have one call, but I might still keep a number. I might call 2 times, I might not give up this number, right? So the graph for this kind of thing, right, is going to be like this. So your x value, sorry, your dependent variable x value, which is independent, is going to be a discrete data. Your y value will be categorical. So at what point of x you give up your phone? Okay. So this is called as, this is basically what we try to do is, we try to predict the probability that y is going to be that you give up your phone number using different values of x. So you basically use a softmax to do it. So it will be a curve, but it will be a curve like this. At one point you give up, right? You try to predict that. Am I making sense, everyone? How a logistic regression works? Yes? Clear, everyone? So in a softmax, what happens is you basically put a threshold value. Anything more than the threshold, you basically round it to 1. Anything less than the threshold, you round it to 0. Okay. By default, the threshold is 0.5, but you can change the threshold. How many of you are understanding this? I understand Niharika is basically putting great descriptions, right? I'm basically trying to understand, help you understand how you read these curves. Yeah. Everyone clear? How many of you are following? Okay, clear? So here you can see this last graph is nothing but a regression line. So what I have done, I am predicting y based on different values of x. Okay. Okay, so 5 more minutes, then we'll take a break, guys. Yeah. Admin, you have a query. Let me know. What is your query? Yeah, tell me. What is your query? I've asked you to unmute. Yeah. Tell me. What is the query, admin? Okay. So let's understand the data type and what type of graph. Okay. So if you are having a categorical data, what is a categorical data? Basically, you are having data like this. Okay. Categorical data means I'm having black ball. Okay, I have a black ball. I have a green ball. Okay. So you want to understand, then you basically just do a frequency table, right? So whenever you are having categorical data, you can do a bar graph. I can also put this graph like this, right? This is black ball. This is green ball, correct? So whenever you are going to have categorical data, it can be color, it can be model, brand names, product names, payment mode, wherever your data is going to have counting. Okay, you can only use a bar graph or a column graph. You can also have a pie chart. You can also have a stacked, you can have a 100% stacked column chart over time. Is it clear what kind of graphs you can do with categorical data? How many of you are following me? You cannot do a mean, you cannot have an average, you cannot have a median. Okay, you can have a mode. Yes, you can find out which is the color which is most repeated. So here you know that it is green, right? Because it's having higher frequency. So the mode might also be that we don't know. We have to put it in some order and check. Okay, clear? What is the ordinal data? How many of you understand ordinal data? Now we are coming to this data, ordinal data. How many of you understand the ordinal data? So this data, how many of you understand what is an ordinal data? So I think most of you buy products on Amazon, right? Then you select your size. So your size can be what? Extra small, small, medium, large, extra large, right? So whenever you are having this kind of data or you are having a rating system, please rate the presentation on a scale of 1 to 10, where 10 is excellent and 1 means very poor. So these kind of data are called as ordinal data. Okay. So what happens when you having this kind of data? So I can also, you can see that I can also do a ranking here. I can do a counting, I can do a mode, okay. I can do a ranking, but I cannot do an average, right? So for example, based on the sizes which are available, can I find the average size? No, right? I can only find the what is the size which is most bought. Am I making sense, everyone? So again, you can see that we can do a bar chart, we can do a column chart. Clear? Yes or no? Education level, yes, very good. Gender, correct? Yes. So I'm also trying to tell you why you cannot do an average. So if you're having, let's say I'm representing this extra small as 1, okay, small as 2, medium as 3, large as 4, okay, extra large as 5, extra large as 6. Can I do an average of that? It does not mean any sense. Yes. Customer satisfaction also, correct. Clear? Am I making sense, everyone? Okay. I think everyone has understood ordinal data. Is there anyone who has not understood ordinal data? Raise your hands. Then we look at numerical data, that is counting data, right? What does it mean? It means quantity sold, right? Or number of questions answered. I cannot sell half a quantity, I cannot sell quarter quantity, correct? Or I cannot answer half a question. That and all is not ideally. How do I count it? I don't have anything like that, correct? So generally in finance, this is very, very, very important. So what does this mean, guys? This means I can count these numbers. Now, what is the difference between ordinal data and numerical data? So like I told you, in ordinal data, correct, I basically cannot find the average. But in this numerical data, I can find the average. So I can say that whenever you find an average, so you suppose you had like 100 questions and you find that on an average, I'm getting something like 49.6. Basically, you're trying to say that people have answered 49 to 50 questions on an average. Okay. So here, I can find the median, I can find the mean, I can find the mode, I can count. Am I making sense, everyone? This is not measuring, guys. This is basically counting. Discrete data is counting data only. It is the number of items sold, or it is rank. So rank will become ordinal data, right? So or positive marks or age, completed age. So today you and I, we basically measure age in completed years. We forget the months, we forget the days, right? So if I'm looking at age in completed years, that is also a discrete data. Making sense, everyone? So here again, I can use a pie chart, a column chart, a bar chart, okay? I cannot use a line graph basically. Here I can also use that histogram, which we had, no? So you can say how many of you are aged 20, how many of you are aged between 20 to 30, how many of you are aged between 30 to 40. So like this, I can do a histogram also, discrete histogram. Is it clear? Is it also clear how numerical discrete data is different from ordinal data? Yes. Okay. Now let's come to numerical data. So when we say numerical continuous data, this is the data that you measure. Okay. This is the data that you measure. So you can do everything for this. You can do a mean, median, mode, range, standard deviation, variation, everything. Okay. So the graphs also, all the graphs that we discussed, we can do on this numerical data, line graph especially. Following? How many of you are following me? Okay. Then you have a Boolean data. A Boolean data basically means what? Yes, no. So we were talking about logistic regression, right? So in this logistic regression, you basically had y to have one of the two values. That is a Boolean data. So either you are going to keep the phone number or you will give away the phone number. So either you will continue to have buy the product or you will discontinue to buy the product, right? These kind of data are called Boolean data. Here we can basically do either a bar graph or a pie chart. We cannot do anything else. Clear? Student enroll. Yes, no. Correct. Very good. Yes. So these are all Boolean data. Okay. Then you have the date data. So date data is basically the date for the line graph. So whenever you have, let's say, product sold, number of units sold, you also have the date. So a line graph generally is used here. Area graph can also be used here. Is it clear, everyone? So the data type, what kind of analysis is valid and what kind of graphs? Have we mapped everything? So where can I use a scatter plot, guys? So when I'm trying to do the relationship between numerical data discrete and numerical data continuous, I can do a scatter plot. When I'm trying to find the relationship between the ordinal categorical data and the numerical continuous data, I can use a scatter plot. Clear? Yes or no? Is the scatter plot logic clear? Regression line again. I can do it with categorical and numerical. I can do with categorical, ordinal with numerical, numerical discrete with numerical, continuous, numerical continuous with numerical continuous, Boolean with numerical continuous, right? If I convert date as, 1, 2, 3, right, which is in a order, ordinal data, I can do that also. Am I making sense, everyone? Is the concept of what graphs to use, what kind of data type? Anyone having any questions? Okay, so we are going to take a break. So we are going to take a 10-minute break. Okay, today the attendance will only be sent by 8:45. So please come back to the session. So now the time is around 8:10. We will resume at 8:20. Is it fine, everyone? Okay. So now it is 8. So we'll be back by 8:20. So kindly come back, guys. Today our attendance will be given to you only by 8:45. So you have to come back and attend the session, okay? So if you have any queries, meanwhile, you can put on chat. I will be answering. I'm just going mute. Hey, welcome back. Are you guys back? Yes. Great. Okay. So we are going to do now statistics in Excel. Okay, everyone. So before we go to the some of the tests that we discussed about, I want to basically give you this very interesting thing, which is called as the Anscombe's quartlet. So what is great about this data set? You can see I have got 4 different data sets. They look very different on graphs, correct? But you will find that all these 4 different data they have the same mu, that is the mean, and the same standard deviation. You can see that the average for all this data is something around 8 is my average. Okay. And my standard deviation, I think, is around 2. Okay. So you can see I basically have all kinds of data here. So here you can see this is a data where I have a linear relationship between x and y. In the second data, you can see I have a polynomial relationship, right? So it's not linear, it's a non-linear relationship between x and y. Basically, this is y. Everywhere, this is y and this is x, okay? In the third data, you can see that I basically have an outlier defining this relationship between x and y. Fourth, you can see that I basically have a single, basically there is no relationship between x and y. One outlier is basically influencing this data, right? But if I simply look at the mean, the standard deviation, you will find that it is the same. So basic statistics is not good enough. I cannot simply look at the mean, median, average only. Okay. You have to look at the graphs. You have to look at the correlations. There should be certain analysis that you have to do to understand the graph. So histograms or the distribution curves, right? These hence become very, very important. So is this concept clear to everyone? Why basic statistics of just mean, median, mode is not good enough? Clear? Yes. So this is also one of the reasons whenever we look at graphs, we also try to put the different statistical measures around it so that we understand it better. Okay. Yes. Everyone clear? And this is also the reason that whenever you are going to do any kind of prediction or you are trying to do any regression or any other kind of thing, you try to select the columns. You will not take all the data and just run, a regression or something. You will try to select which among these columns is more important than the others. Making sense, everyone? Yeah, that's correct. So you can see that the mean data is the average of everything, correct? So if you look at all this data, you will basically, this is a representation. This is a very well-known concept. You can go to Wikipedia and you can actually type this Anscombe's quartlet. Okay. You will get 4 data sets. This was actually found by this scientist called as Anscombe. He identified that, just looking different data sets can have the same central tendency measures. So hence graphs is very, very important. So this is also the reason that we do a lot of these graphical representations, okay? Whenever we are trying to craft a narrative also. It's not good enough just to calculate and put the numbers. You also need to look at the relationship between different variables. Am I making sense, everyone? Okay. So this also tells you another thing, right? That maybe the numbers that we are talking about, like the means that you are comparing, it might actually be the same number, but depending on the kind of data you're deriving, they will not be equal. Okay. So hence we are going to do some statistical test. So to do the statistical test, we are going to take this Excel sheet. The sheet is called statistical test underscore day 5. I want all of you to download it. So I'm going to just share my screen. Okay. So this is the data that I have got. You can see it has got different data, right? We're going to do some statistical test here, guys. So please download it from your LMS, all of you. Let me know once you have downloaded. Okay, so I'll share that file here also. So I've shared this data here also. Others, you can see I've shared it here, correct? So please download. Once you have downloaded, please put a thumbs up or something so that I understand. I'm going to give you guys 2 minutes to download this file, either from LMS or from the chat window. Everyone downloaded? Only one person has replied to me. What about the others? Okay. So if you are downloaded, we're going to start with this. Okay. So we will directly go to the first sheet. So what is this? These are basically, you can see there are two columns. Everyone has downloaded this data, right? Okay. I'll give you 1 more minute, guys. Then we will start with these different tests that we are doing. Okay. So Nalini, have you downloaded it now? Done? Okay. So here you can see that let's go to the first sheet. Okay. So you can see that these are basically different payments. One column tells what is the different payment using UPI. The second column tells me what are the payments using card, credit card. Okay. Credit or debit card. Okay. So these are the payments. You can see there are different numbers and we have taken these averages. Okay. Can you see this? So how do you calculate average? You basically say equal to average this array and you say this is the average this array. Okay. Now we know that these numbers do not look the same, right? But how sure I am that these numbers are never the same. Okay. So you can see that I'm going to compare these numbers using t-test. Why I will use a t-test? When do we use a t-test, guys? So a t-test helps me to compare between two averages when I have a very small sample. So here you can see I have got how many samples? I just have 10 samples. Okay. So I've got 10 UPI transactions. I've got 10 credit or debit card transactions. Okay. And I have got some averages. It looks like these averages are not the same. Okay. But I want to check this at 95% confidence level, right? Whether these averages are the same or are they different. Okay. So how we will do? We can go to formulas. Okay. Here you can see there is something called as more formulas. So you have to go and select the statistical formula. In this, you can see that you get something called as a t-test. Okay, so let's go down. You can see t-test, right? Okay, so select this t-test. Here you can see t-test. So you have t distribution, 2t, t distribution, rt, sorry, right? So we have to select t distribution. Below that you can see there is t-test, right? Select that. So what is this t-test actually going to tell you? You select this array, okay? Then you select this array, okay? Then are we going to do a one-tailed? Yes, we are going to do a one-tailed distribution, okay? So are they paired or are they not paired, okay? So we are going to do them as paired, okay? What does it mean? Paired means that the same person did a UPI also, he has done a credit card also, or maybe we will not even do paired. Let's do unequal variance to sample. Okay, so there are two independently done transactions. This is done by a different set of people. This is done by a different set of people. Okay, and they have different variance also. Okay, so how do I know this is the average? We can also do the variance if you want. So this is what stand, and I can just select this. You can see this is the variance here and this is the variance here. You can see the variance are different. That is why I have selected this, right? So what did we select? So you can see there are two sample unequal variance. So that's what I have selected because you can see the variance which I calculated above is not equal, right? So what is the t-test value? Can you see this t-test 0 is 0.02? Okay. So if this t-test, this value that you get is less than this alpha value, it means that these averages are completely different. Okay, am I making sense, everyone? Suppose I change this value. So you can see I actually increased it, right? Look at the p-test value. Has it become smaller? It's 0.006. It is less than this. So you can see that. So maybe I should decrease some of the values, then we can check. So what I'm trying to do is I'm just trying to, can you see guys now? You can see I have got two sets of transactions now. I have done some changes. You can see I have just removed 500, 400 and all, right? I have an average which are very similar to each other. Can you see this? This is 1046 and this is 1115. Okay. Now what I did, I basically changed some values. Okay. Now you can see I have done the t-test again. I have just changed these values automatically calculated. You find this t-test is now greater than this alpha. What does it mean? It means that these averages are comparable. So although this UPI average is 1046, this credit card average is 1215. You can see it's 1215. These numbers are not very different. They are comparable. Am I making sense? Is it clear? Hello? How many of you have understood what we have done? So in your data, you will find that they are very different, right? I had just changed some numbers. I'm just trying to show you that they are no longer different, even though it looks like it's different, right? Similarly, I can check for variance. How do I check for variance? So I again go to this statistical functions and I have to now select the F test. Can you see here F test? Select this. So in F test, what are the things that go inside it? So you take the first array, then you take the second array, right? And you press, sorry, you can see. So I have the F test, first array, and then second array, and then press enter. So what is the problem here? Okay, I've selected it. Can you see it is showing me some number which is very, very small. So in Excel, when the number is less than 0, right? This number is basically 0.000 something. Okay. That's why it is showing like this. So if I do like this, you find that it's a very, very, very small number, right? So what does that mean? This is less than this alpha, correct? That means that the standard deviation for these numbers is very, very different. You can see also. So if you want to compare the standard deviation between two numbers, what do? We do the F test. Is it clear, everyone? Alpha is basically the significance level. Okay, it's 5%. I have set it at 5%. Okay, suppose I change the alpha to be 1%. Okay, this is a number that we fix. Okay, so at 99%, okay, I'm checking whether this data is different. Now you look at this at 99%. Okay, so I will compare now my t-test number against 0.01. Okay, generally we put it at 5%, but at cases which is very, very common, right, we also take a 99%. Okay, so this alpha depends on how this data occurs in nature. So for example, if you look at the use of soap, toilet soaps in India, right? Almost 90-95% of all people use toilet soaps, isn't it? So I can definitely fix my error rate or alpha at 5% or 1%, okay? And I can compare the numbers. Suppose I am checking for diabetic drugs, right? So in India, around 50% or 30% of the population has diabetes, right? So I can actually fix this alpha at very high level then. Maybe I can fix it at, 20% or 30% also. So then I will compare it with 0.3. Suppose this is for diabetes, okay? So if I'm comparing the drug use among diabetic people they paid using UPI versus credit card, I can actually fix a higher rate. Then you will find that this by t-test these numbers are this is less than this, right? So they are different. So at a 30% alpha or a 0.3 alpha level, you find that this average or the payment done by diabetic people using UPI is significantly different by the payment done using credit card. Okay. So this depends on certain categories. We fix this number. Is it clear, everyone? Am I making sense? What is alpha? Yes. Alpha is a number we fix. Clear? It's a significance level. Yes. So basically, here you see, right, at 0.05 level, you find that the t-test value is greater than this. That means that this 1046 is not significantly different than 1215 at a alpha level of 5% or a 95% significant level. So at 95% significant level, these two are comparable. Am I making sense, everyone? This is how you interpret it. This is how you talk about this. Clear, everyone? Is t-test making sense to everyone now? Okay. Now F test, you can see it is simply, okay, so now let's change all of this. Okay, now you see guys, you can see I have just changed some numbers, right? You can see now your t-test value is greater than alpha, your f-test number also is greater than alpha. Can you see that? This is nothing but 0.7. E0 minus 0.1 basically means this is 0.7, which is greater than 0.05, right? T, so you will find that when I have changed the data, right, these two variations are comparable. These two averages are also comparable. Can you see that? So rather than scientific, just put it as a number. You get this number now. Yeah. Is it clear, everyone? Making sense? Guys, there are some people who have just joined for attendance. I think from tomorrow, we will not let anyone to attend after 8 o'clock. Okay. Does not make any sense. There are only 250 people or something till 8 o'clock. Okay. So is this making sense to everyone? So are you understanding t-test? Are you understanding f-test? Okay, this is going to be the most common test that you will be doing. That's why I'm showcasing this. So you are going to get the attendance link only by 8:45 or later. So please wait. Now let's go to the Z test. When do we use a Z test, guys? Okay, we will repeat t test again. Okay, when do I use the t test? I use the t test when I want to compare the mean or the average between two sets of data. Okay. And the number of data points I have is less than 30. So here I've got only 10 data points. Okay. So I want to compare these. You can see that I've got the first average as 1346 and the second average is 1017. It looks very different, right? So I want to see whether they are different. So what I do a t-test. You can see I have just put the formula here. And you can see that my t-test value is 0.17, which is greater than my alpha value of 0.05. And hence, what is the conclusion? The conclusion is that they are not significantly different. We can say that they are comparable. These averages are comparable. It seems to be similar. F-test is when I want to basically compare the standard deviation. So when I basically want to compare the standard deviation, right? Okay, what do? I basically do a F-test. So what is the formula for F-test? I select F-test from formulas, other, statistical, right? And I put the array 1 and array 2. So you can see that the standard deviation is 710 and 797, right? So they seem to be different. There is almost a 80-point difference. I did a F-test. Can you see it is 0.74, which is much greater than 0.05. That means that they are also similar. They are not significantly different. They are comparable. So now let's change something and check again. So you can see now the standard deviation is what, 491 and 797. Can you see my F test is 0.17? That means it's much greater than 0.05. That means at 95%, they are not significantly different. Is it clear? Got it? and ANOVA are not the same. I'll show you an ANOVA now. The next thing we'll do is an ANOVA. So have you understood the F test and the T test? Yes? Okay. Let's go to ANOVA since you want to know ANOVA. So go to sheet number 3, which is labeled as ANOVA. You can see that I've got 3 groups here. You will use an ANOVA only when you have 3 or more groups. Okay? You do not do an ANOVA when you have 2 groups. When you have 3, 4, 5, 6 groups, you do an ANOVA. So the way you do it is, again, I fix an alpha. I have fixed alpha at 0.05 or 5%. So how do we do an ANOVA? We select the data. We go to data. So here, how many of you have got data analysis here in Excel? So here again, you can see I have got many things like T test, Z test and all. You can see that. So here you can see I have got ANOVA single factor. I select it. Okay. Now it's going to ask me for certain data. You can see I can put the input range. So I've taken A1 to C11, right? So how we can select it? We can select it again like this. Suppose I'm going to put only till here. Okay. You click it again. It takes it. It is grouped by every column is a different data group. Okay. Labels are in my first row. Yes. I'm fixing my alpha to be 0.05. I have put my output. Let's change this. Let's put for the new data here. Okay. Then I say okay. Okay. You press an okay. Can you see I have got this ANOVA? So how do I read this ANOVA? I basically have to look at this p-value. Okay. I look at this p-value and I compare it against 0.05. If this p-value is less than 0.05, right? So what does it mean, guys? You can see it basically means that there is at least one group which is different. So there is one group which has an average which is different from the other groups. That's how you read it. Another thing you do is you can compare your F value with your F critical. This value should be greater than that. Okay. So you can see that my F value is definitely greater than my F critical value, right? So 38.9 is greater than 3.466. So I can confidently say that. So you can see that I have basically taken less data here, right? So there is at least one group which is different from the other group, the average of one group. So ANOVA basically it looks like this. What does it do, ANOVA? Basically, what it is going to do is, it is going to look at clusters of data. ANOVA basically tells me that one cluster looks to be much farther than the other clusters. Am I making sense, everyone? Is ANOVA clear? How many of you understood this? How many of you are not understanding this? Yes? So guys, you can see Amar has shared the attendance also. So you can use that link also. Okay. So we have done T test, we have done F test, we have done ANOVA. Clear, everyone? Okay. So let's come to ANOVA. I'm going to draw how it looks like so that you understand what it is. Okay. So we did T test, right? Let's come to whenever you are having 3 or more columns, you use an ANOVA. This is what I was telling you. So basically, what we are trying to do is I've got a set of data, right? So in ANOVA, what we are trying to do is we are trying to understand whether these data are nearby or are they close. That's what we are trying to do. So what this particular test does is it basically tries to group all the data which is nearby with by representing it with the average of this data. So I take the average of this cluster of the data x1. I'm comparing the average of this cluster of data x2, and I have this third cluster of data x3. Okay, these are all my means, or let's put it as nu1, nu2, and nu3. Okay, so the ANOVA is trying to tell me whether these nu1, nu2, nu3, right, are they comparable or are they different? That is what my ANOVA is telling. Okay, so once I do this ANOVA, I just told you how to select. I can go to data analysis. I will press ANOVA single factor. Okay, so there is no replication of data, right? So the data does not repeat is what I have taken. I said okay. Now I simply compare my p value which is there with this alpha number. If this p value is less than this alpha value, then the way I should say is that these groups have at least one group which is different. So these three groups are definitely not the same. Why? Because there is at least one group which has a mean which is significantly different than the others. You can see it is not saying that all the three groups are different. We're only saying that all the three groups are not comparable. Am I making sense, everyone? Is it clear? ANOVA is clear to everyone? How many of you did not understand this? Okay, Manu Francis, you have to go. I don't know whether you are using Excel. You have to go and so if people who are not having this, go to you have to go to the outside. You can see there is something called Excel add-in. You have to go here and you have to select this analysis tool pack. Okay, only if analysis tool pack is there, you are going to basically have this when you go to data, this data analysis. Okay. So this data analysis you have to select. Making sense? How many of you understood ANOVA? Yeah, you have to go to data analysis only. It's not there in formulas. Okay. How many of you understood ANOVA? Okay, so this is ANOVA, guys. I'm going to repeat this for the last time. Okay. So what is ANOVA going to tell me? I have got three sets of data, right? This is one set of data. Maybe this is another set of data. And maybe this is another set of data. Okay. So ANOVA is basically trying to cluster this data. How do I cluster it? I'm basically trying to, so it gets the average one, okay, average 2, average 3, okay. I am comparing these three averages. How do I compare it? Using ANOVA, okay. So once I select this ANOVA, I compare this p value with this alpha. If this p value is less than this alpha, then what do I say? I say that there is a high chance that there is at least either nu1 or nu2 or nu3 are not same as the other. So it looks like there is at least one group which is different average than the others. Is it clear how you read ANOVA? Making sense? Is it clear? Okay, so there is someone who wants to understand. So the t-test also basically is what I have got very less data, right? So I have got less data and it looks like these numbers are very different. So I want to check whether these, so you can see on the screen, if you see my screen, right? I have got some 10 different data points of UPI and card. So it looks like the UPI average is 1046. Card average you can see is 1715. Okay. I have done a t-test. Alpha is 0.05. Look at the t-test. The p-value is 0.35. Evan, can you see this? What does this mean? It means that basically this 1046 is not different from 1715. That's what we are trying to say. Okay. They are not very different. They are not significantly different from each other. That's what we are trying to say in t-test. In f-test, we are comparing two variations. So basically, you're looking at the dispersion. You're not looking at the mean. You're looking at the dispersion. Okay. And you're trying to say whether this dispersion is comparable to the other. Are they the same or are they different? So why we are saying all of this? Okay, because these are independent data, right? So you have a normal distribution. Okay, it's possible that the UPI data, I accidentally have got this part of this data. The card data have accidentally got this part of the data, but they are the same curve. Am I making sense? This is what t-test is trying to say. It's possible, right? Accidentally, because I have got only 10 data points, all my UPI data points are from here. And all my card data points are from here. Basically, I am representing the same curve. This is what I am doing using the t-test. Clear? F-test, you are basically looking at the alpha. Okay? Am I making sense? Clear? What is t-test stand for? Everyone got it? T-test, F-test, ANOVA. Attendance link is already there, guys. You can see this. I would request Amar to once more put the attendance link here. Okay, so we are almost done. Maybe we can look at regression tomorrow. So how many of you thought that today's class was interesting and you learned something? Please put a thumbs up, everyone who thought this was useful and you've learned something. Okay. So Manu Francis, did you manage to download data analysis? Okay, cool. All right, guys. So thank you. With this, we end today's session. Tomorrow we'll be doing pivot tables, pivot charts. Okay. So please come on time. All right. Thank you, guys. Thank you. Bye-bye. So attendance link is here, guys. You can see here. So I'm just gonna so you can see Amar at 8:58 p.m. he has put the attendance link. Amar, can you put the attendance link for the last time?
Yeah, sure.
All right, yeah. So thank you, guys. Let's meet tomorrow. This is the attendance link. Use this. Okay, with this, I'm going to end the session. Thank you. Bye-bye.